Welcome everybody to my talk about Spring Boot 3 and Spring 6. Talking about what is new in this next major release of Spring. And I'm very fortunate to be here today because this talk is extremely relevant at this current time because Spring has just recently released the first release candidate for Spring Boot 3. This was just 2 weeks ago. So everything that's going to be released has just kind of been finalized. We now have a full overview of all the features that are going to be there. There will still be bug fixes likely and maybe some polishing, but this should give you a very good idea of what to expect when you upgrade your application to Spring Boot 3. And just out of curiosity, I know the whole hands thing is kind of not great, but I wanted to know how many of you knew that Spring had a new major release coming up prior to? Okay. Awesome. So you guys do keep track of that. Well, hopefully you all have some experience with Spring. You don't need much experience, but if you just have the basic Spring Boot 2 knowledge, you will be able to follow everything that we're going to do here today. But first, let me give a little bit of an introduction. My name is Lennart and Wolde. I'm a software engineer working for Gillit. We are a sponsor at this conference here today. We are an organization that is by developers and for developers. So I think that's something that makes us very unique, where everybody in the company is, even currently, is actively developing. So it's a very fun culture. And we like working with quality software and having a quality relationship with our clients and working with the latest technologies, such as Spring Boot 3. In order to solve real-world problems. I currently work for KPN IoT as a backend Java developer, where I work in a team that exclusively uses Spring for backend solutions, and we only do backend development to solve problems in a complex landscape with lots of high-volume data coming from the IoT space. So without further ado, let's take a look at the agenda, everything that we're going to talk about today. On the agenda, first of all, are the breaking changes. I want to quickly mention what changes might cause your code to break and might prevent you from upgrading. This is a breaking release, of course, because it is 3.0, so there's some of them. Then we're going to take a look at HTTP interface client, which is a new way of making blocking and non-blocking interfaces for external HTTP APIs. We're going to take a look at support for RFC 7807, which is a standardized specification for dealing with API errors. Then we're going to take a quick look at observability, which is a new unified API for managing your application monitoring. And then finally, I think the big new feature, native image support with crawl VM. This used to be part of the Spring Native project, but with Spring Boot 3.0, it has been fully integrated into Spring Boot itself with a lot of improvements and quality of life, things that make it easier for you to start using this new technology with your application. And then to round this all off, we're going to do a little bit of a migration of a live project. I'll have to watch the time. Hopefully I can show you how it works to migrate a Spring Boot 2 project to Spring Boot 3, so you can see just how simple, hopefully, it is to start using all of these new features. Okay, let's start with the breaking changes. So Java 17 is now the minimal requirement for running Spring Boot 3. This is, of course, done for future compatibility reasons. There's a lot of nice developments going on in the Java landscape, and to be able to utilize all of these, the support for the really old versions have to start being dropped. Java 8 is very, very old at this point. And therefore, they've decided to drop support for both Java 8 and 11. So if you still happen to be on an old version, that is a breaking change for you. Then you also have Jakarta EE9, which is the new version of the Enterprise Edition specification, and there will be some downstream dependencies that also have breaking changes that are part of the new Spring Boot upgrade. But that depends, of course, on your own application setup. So Java 17, like I said, support for Java 8 and 11 has been dropped. And they also removed the Java SE Enterprise Edition module from the Standard Edition Java. This contains some Enterprise Edition APIs that were just available for everybody to use. This won't affect most people because I believe this is only for JAX-B, so the XML processor, and maybe there was JAX-WS as well. These are now available as just regular dependencies on Maven or Gradle, so all you have to do is just take those in. And then, of course, there are some dependencies that you may have to upgrade for compatibility with Java 17, particularly if they do some low-level unsafe work. Then Jakarta EE9. So this has been rebranded from Java Enterprise Edition for political reasons that, quite honestly, I don't even fully understand, but it's also not really relevant to us developers. What does matter is that as part of this rebranding, the package structure, JavaX, has been renamed to Jakarta. So obviously this impacts us developers when we use servlets, Java Persistence API, and even inject annotations. You'll have to change that, but particularly this had a major impact for the framework itself. So there's a lot of improvements under the hood for Spring to work with Jakarta. Also, there are some dependencies that have a version for both Jakarta and the old style packaging, which means that you will see some dependencies be suffixed with -Jakarta to indicate that this is the Jakarta version, which you'll now have to use. So you should check your POM XML and build.gradle to make sure that all your dependencies are still managed by Spring, and you're not using an unmanaged dependency. So that's all of the breaking, well, most of the breaking changes. Of course, the exact list of them depends on your own setup. But now that we've had this annoying part done with, it's time to get to the good stuff. Which are the new features. And to start that off, we've got the Java interface clients, which is a way you can define an interface for an HTTP API. And then Spring automatically implements this for you, just like they do in data repositories. You can use this with a Webflux web client as a backend, but of course there will be more backends available later. This is just the one that's available for now. But don't worry, you can use it both blocking and non-blocking. So all you have to do to make use of the blocking API is just treat it like a regular API where you have voids or direct return types. To use it reactive, you just use mono and flux. So this is what those interfaces look like. You have an example here of a client where you can see that the annotations are heavily inspired by what Spring is using for REST controllers, with the main difference being that instead of mappings, because you're not really mapping an endpoint, well, in a sense you are, you have exchange annotations. This is much like the RestTemplate exchange methods. But other than that, the way you interface with these clients is very, very similar to REST controllers, which I think will feel right at home to most Spring developers. You might notice this is somewhat similar to the way OpenFeign looks, and it is, but of course the main difference being that this sticks closer to the Spring terminology. So you define your clients like this, and much like a data repository, the implementation is generated for you. So how do you create that implementation? You just define a proxy factory where you can specify the backend, so the client that has to power your client interface. In this case, we're just constructing one using webclient builder, which uses the Webflux web client. And you set the base URL there, and then you can use this to create any number of clients that are powered by this backend. So we define a second bean, a to-do client, that creates a to-do client from that factory. And then you can just auto-wire this right into your components, like so, or with constructor auto-wiring, of course, and use it as you would any other function. So that's the Java HTTP interfaces. Now we have RFC 7807 problem details, which is a standardized machine-readable format for detailing error messages in an HTTP response. Basically, it tries to solve the problem that in traditional applications, you can display your errors directly to the user because you're rendering HTML. Well, with APIs, it's a bit different. You cannot display any arbitrary format. APIs have contracts. So how do you design an error response that the client understands and can do something with without having to jump through a lot of hoops that you may currently have to? Of course, there are existing libraries that implement this as well, but this solution has been integrated very deeply into the Spring ecosystem. And they created this in the so-called problem detail API. So before we go there, though, this is just a sample endpoint from a to-do application. This also show this later in the demo. We'll convert this, which has a simple post method that gets something out of a repository, and maybe you're doing some business logic to check if the amount of to-dos in a project exceeds a certain maximum, and then you want to throw a custom error. This is very typical web MVC exception right there. And maybe there's not allowed to be more than 10 items because maybe the front end cannot render more than 10. Maybe it's made in jQuery. I don't know. Or perhaps it's your list of chores, and who wants to have more than 10 chores on their to-do list? So what does Spring return when you run this code in Spring Boot 2? You get the following response. And the problem is that this is not very useful to the client. Using this information, there is absolutely no way you can derive what went wrong and how to solve the problem. So what do you do when this happens? Well, you might define a custom error DTO, and you might communicate that to your API consumers. You have this DTO, and you have to be able to parse it this and that way. And you might even document this on OpenAPI, have a Swagger page running. And these are all good ideas and good things to do. But you are, to some extent, reinventing the wheel. And RFC 7807 is just a way of standardizing these error responses. So it's standardized, self-documenting, which means that you just get the JSON output, and anyone should be able to tell what went wrong just from the content. You don't need extensive knowledge of the format. And it's extendable, so you can add custom properties to allow consumers to solve problems in specific ways. Here's an example of what that looks like. Let's break this down a little bit. First, you have it's a standard HTTP 1.1 response with a 403 forbidden code. You can use any status code you want. Followed by the content type application/problem, so not JSON, plus JSON to indicate that it has been JSON encoded. You also specify the content language to indicate which language the error messages have been are presented in. And then there's some standardized fields inside of that. First, you have the type, which defines the type of error, which is a URI, either relative or absolute, that points to a web page and that will explain or show a human-readable explanation of what this error message is and how to solve it using the information available in this error response. A title, which is explains the type of error as well, but in a human-readable way, in case you don't want to go to the URL to figure out what type of error this is. And details that contain specific information about this instance of the error. So here, if there's an error where, this is an example that comes from the specification, your balance is only 30, but you're trying to purchase something for 50, those kinds of specific details go in here, because the title should not be different depending on the instance of the error. It should be the same for all instances of a specific error. And then the instance explains where this issue occurred, which is also a relative URI. And then there's some custom fields that can be added to the response as well that the client can use based on the type. Apologies, wrong button. Based on the type that was specified. So to use these, it's actually rather simple. All you have to do is define a controller exception handler, which is a controller advice. This is not new, and you can extend the response entity exception handler. This is new, which automatically defines error handlers for all of the standard Spring MVC errors and handles them using this new API. So all you have to do is add this, and you will integrate with it. But then what you get, if you were to run the exact same code in Spring Boot 3, is this, which is perhaps not much more useful than the original error, because the true value comes from when you fill out these problem details yourself, like so. Let's go back to the exact same code from before, but now we're defining the details of our problem detail in the standardized problem detail object from Spring, and you can see you create it for a specific status code that you want to return. You define the type, which again is a URL, title, and detail, which was what I was injecting as the exception message before. And then you return a error response exception with the response code, the problem detail, and the throwable. But because this is a custom exception, we just use null here. And if you run this code, well, now you get the following result, and this is much nicer to the consumer. If you get this error back from your API, you can immediately tell what went wrong and how to solve it. Right? You know that the max items per project have been exceeded. You know that in the project chores, there's a maximum of 10 entries, and because you're trying to add an 11th one, it's not working. And now the client has much more information to work with on how to represent this information to the end user or solve this problem in the consuming application itself. Of course, you can also use exceptions, either your own exceptions or ones from dependencies that you use. This is just a regular exception that holds some data. And you can, inside of your controller advice, you can define a custom exception handler using the exception handler annotation. And then you can return a problem detail. This is new. And if you do this, Spring will automatically handle this and return the problem detail according to the specification as the API error. You can then move your code over to here, and then all you have to do is just throw your exception in your own code and manage it that way, and you'll get the exact same result. So that's problem details. The next thing I want to talk about is observability, which is a new feature of Micrometer that was introduced in Spring Boot 3. Some of you might be familiar with Micrometer from their other APIs. You can use Micrometer for metrics primarily. Some people may have used the timed annotation. That is part of Micrometer as well. And before I go into that, just a little example of a random monitoring dashboard, right? Application monitoring is very important for any production Spring application or any application really. We often have to collect a lot of different metrics that we want to show to give a diagnosis when there's a problem, such as throughput of our request, the latency, all kinds of different statistics. And we need to make sure that our applications deliver all of the required metrics for this to work. And on top of that, we often also want to be able to trace specific bugs. You know, if a certain customer comes to you and says, I have this weird bug, then you should be able to look up for this customer exactly what happened in their session. So that's another layer that's added on top of this, and it can get rather complicated because in the application monitoring, you have your logging, of course, so you can see what your application is doing. You have your metrics to get information about how the system overall is operating and how the performance is. Including error rates, throughput, latency, but you also have your tracing. So how do you interface with all of these different components in Spring? Well, most of you will know to log, you use SLF4J. For metrics, you can use Micrometer with all the annotations that are made available to you. And for tracing, you had Spring Sleuth, or Spring Cloud Sleuth, which has now been succeeded by Micrometer tracing, a new feature in Micrometer. And you might notice Micrometer is starting to take on more responsibilities, and there's a lot of overlap between the tracing, metrics, and logging. So observability is a new API that is designed as one API to rule them all, kind of. So it does metrics for you, but also tracing and log correlation, so that when you're tracing a specific user request, you can not only see how long each request took and what went wrong and all of the information available from your metrics, but you can also see the logs that were logged during this user's request. It's automatically correlated and very deeply integrated into Spring, so it requires relatively little configuration. There's a blog post on the Spring website on how to implement this with Loki and a bunch of other backends, because there's multiple underlying implementations you can use. You can use tracing in Zipkin and open tracing. They're both supported as bridges. And of course, you have multiple metrics registries. It works with Prometheus as well as Graphite and a bunch of other ones as well. There's actually a lot of different metrics registries you can choose from, even distributed ones. But the idea is that you have one API that you use as a Java developer to handle metrics, tracing, really monitoring in general, and then the underlying implementations can just be configured. So how does Spring integrate with this? Well, they automatically instrument your REST template so that if you have a client that is making an API call to some, or to another API, you have one API that talks to another API, the REST template is instrumented so that the tracing session will continue when the code starts executing in the other API that's being called. So it's automatically propagated so that when you follow a tracing request, you can see in all the different services what happened and how long each of these calls took. You don't have to do any work for this because Spring automatically adds that metadata to your HTTP request. And on the receiving end, so long as it's Spring, pulls it out again and makes sure that it registers under the same tracing session. It also has built-in support for Spring MVC so that all your endpoints already have metrics available for them. And what does that look like? Well, this is an example dashboard from the Spring blog post. It's a bit difficult to read. You don't have to read the actual content. The idea is, though, that you have your logs for this specific tracing request that you're using a trace ID. So you can see all the logs correlated nicely, and here you have two Spring applications that are talking together, a client and a server, and you can see that in the same tracing session, you can get information from both the client and how long that took, as well as the server. So you can also use this to measure your network overhead and get an idea of what went wrong during a tracing session. But the cool thing about this API is, because this API is used for both tracing as well as metrics, is that from the exact same API, from the exact same code, you can also generate your regular metrics dashboards, like the latency for all requests. So this is not talking about a specific request, but taking averages or 99th percentiles over all data, which traditionally you would have to use different APIs for that. Sleuth for your tracing and Micrometer for your metrics. Well, now there are in the same API. So what does that look like? This is an example where you use the observation builder right there to create a new observation. You need to name this. This contextual name is what is used in the underlying tracing implementation that you're using. You need to name it, along with some low cardinality properties. Now, these properties are properties that have a low cardinality, which means there's not a lot of different values associated with this. So these are things that would be useful for your metrics, like you want to be able to get the average request time for each endpoint. So your endpoint, because there's only a small set of different endpoints in your application, would be a low cardinality property. In this case, in my project, I've decided that the project is a good low cardinality property because I only have a few different to-do lists, as well as the action, like how often are items being added or closed. These are metric level properties. And then you can also define your high cardinality key values. These are things like identifiers, like a user ID or maybe a client session ID, something that can easily be referred back to that will be used for tracing. So you want to find the traces for a specific user ID. That's what the high cardinality key value is for. And then in the observe method, you perform some code, and all the logs inside of here will be correlated. If you use a REST template to call another API, that is automatically modified so that the tracing session continues where it's being received, and this is integrated very deeply into Spring. There's also an annotation to do this, which is add observed, similar to add timed, where you can do it at the annotation level. Although the number of configuration properties that you can set is, of course, more limited when you use the annotation. So that's the observation API. A great new way to take care of all your application monitoring needs by utilizing a single API. And now we get to the, I think, probably one of the new main features that is very interesting is the native image support with GraalVM. People have been talking about this for a while, and there are other frameworks that are specifically focused on Graal, but what Spring thought is that this would be a really nice feature to make available to Spring users to enhance the number of use cases for Spring with GraalVM native images. So to give a little bit of background before we dive into the details, this is what typically happens when you write a Java application. You have stuff that happens on compile time. Oh yeah, it's a red cursor, so it doesn't really work. You have your source code, which is being compiled into bytecode, which is really just your source code, but it's parsed and validated and then saved in a binary format. So then if there's an issue with your type, because of course it's a strongly typed language, or there's a syntax error, you would know this at compile time. And there is much less work that has to be done on runtime when you write a Java program than maybe interpreted languages like JavaScript. But there's still a lot that happens on the runtime, because the runtime takes your bytecode, so the binary representation of your source code, and then runs it through Hotspot, which is the virtual machine in which all your code runs. And it goes through an interpreter, and for the people who are very deep into this, I know that it's not just an interpreter, and you also have a lot of optimizations and a JIT compiler, but it doesn't really matter for the sake of this, this argument, which then eventually makes sure that some machine code is ran that your actual CPU understands, because this acts as a virtual machine, so a machine that acts as a machine that understands a uniform format, but can run on, and allows your code to run on every platform. It also contains some tools like your garbage collector and your thread scheduler. But you see that your source code, or sorry, your bytecode still has to be converted to machine code and optimized and JIT compiled. And that takes a lot of time on startup. But with native images, what happens is a little bit more of the work gets done on compile time so that less has to happen on runtime. Now, interesting. What happens on compile time is that other than just taking your source code and parsing and validating it, it also compiles it into machine code already, which means that it will only run on the platform it was compiled for, but the interpreter is now no longer necessary. And if you use native images, you can see that on the runtime, your machine code for your Java is already there, and then the only thing that it also includes is substrate VM, which are basically the other parts of the VM, like the garbage collector and thread scheduler, that are needed for your code to run. But the interpreter is no longer there, so this work doesn't have to be done when your application starts up. Now, this is part of a greater idea that is being promoted, which is to do things ahead of time, which is short for, or long for, AOT, which is the idea that you should do as much work as possible ahead of runtime. So this means generating the machine code. You can do that on compile time. Generating your initializer code as well. So Spring Framework also needs to do more work to make sure that your application has to do less stuff when it's starting up. But also you as a developer need to think, how can I get rid of other bottlenecks that happen on startup? It's really the idea that you should move your work away from runtime to compile time so that your applications can start up faster. Which means that maybe if you're provisioning a lot of different resources, that's extra time that's being added to your startup. So you also need to think about it as a developer. So GraalVM, of course, plays a big role in this because it's the virtual machine that your code will run in. It's based on Hotspot and OpenJDK. It's kind of built on top of it. It supports ahead-of-time compilation, critically, which I showed before in the diagram. The way it works is it finds reachable code through aggressive static analysis. So it analyzes your code to figure out which code is actually going to be executed and uses that to find code that can be reached and should be included in your program, and removes code that can never be reached as an optimization. It then compiles your bytecode to a native executable after the bytecode has been generated, and it combines this native code for the reachable code with the substrate VM into a native image that you can run. But again, it's important to note that unreachable code, so code that the analyzer has found can never be called, will not be included, which means that if you're using things like reflection, so working with annotations essentially, will not work out of the box. It requires a bunch of extra work where you have to specify custom metadata saying that, hey, this code is actually going to be called, so you need to include it. You might already think, well, Spring does a lot of that, all annotations all over the place, and proxies, and component scanning, and a lot of crazy stuff. So surely they should do something to make AOT better and more achievable. And they have. That's the Spring AOT engine. Spring AOT engine optimizes your bytecode for static analysis. So they take it's built into your build tools like Maven and Gradle. It analyzes your application context. So this basically is your configuration for all of the different beans that you have. That's your application context, and it's analyzed on compile time by Spring so that it can generate code that reconstructs this. So it doesn't have to do component scanning. It generates a whole bunch of Java code, think of it like factories, that can recreate your entire set of beans so that your application can run as intended without having to rely on component scanning and a high amount of reflection. Well, without runtime class bed scanning. So why do you want all of this, right? Our current applications are working perfectly fine. So why go through all this effort? Well, if you create a native executable, because the entire Java virtual machine and all your unreachable code is no longer there, you have a much lower memory footprint. But it has also become a lot more dependent on what you actually use. So if you add a lot of different dependencies, different databases that are supported, and frameworks that you're integrating with, and Swagger, and you name it, the more stuff you add, the more of a difference it makes. With traditional applications, that didn't matter as much because the JVM was already so bulky that you don't really notice much if you add a bunch of other stuff onto it. Now you do. So, but if you keep it small, and you just keep the basics in your application, it can result in a very low memory footprint. Under 100 megabytes is possible, which today's modern Java applications don't really run well below a gigabyte. So that's an order of magnitude smaller. It also allows your application to start up much faster because it's done a lot of the work when you compile your application. And a note, that does take a lot longer. It takes about 5 minutes to compile my Spring To-Do application, and it takes a whopping 8 gigabytes of RAM to do so. So it definitely creates some opportunities for going on a coffee break. How fast is it? Well, maybe not on my laptop on its battery, but in a typical environment with a very simple application that has just some REST stuff and maybe some APIs that it's interfacing with, you can get it to under 100 milliseconds, so 0.1 second startup, which is more than an order of magnitude faster than current Spring applications are. It also allows for more aggressive auto-scaling. Because your application starts up so fast, you can be more aggressive in downscaling your application. Because if the requests go up again, you can just spin it up, and within 100 milliseconds, you're ready to take in requests. So that creates interesting new opportunities in the infrastructure world. And potentially, you can even auto-scale it so aggressively that you can scale it down to 0. This depends on your use case, of course. The more you do in your application, the more difficult that becomes, but depending on your use case, it might be suitable for that. So that begs the question, if this is the new way, then are jars being replaced? Are traditional Spring applications no longer recommended? Should we all go ahead and embrace this new native technology? No. Native executables do not replace the JVM apps. Instead, they extend the number of use cases for your Spring applications. There are a lot of times when Spring is perhaps not the best tool for the job, but with support for Graal Native, it can be. So it simply allows us to use our existing knowledge for more different use cases. Is it ready? Well, yes, it is ready. It's actually very simple. No additional configuration is required with Spring Boot 3. In most cases, if you do some reflection yourself or proxying, you should try not to, but if you have to, you need to provide reachability metadata. This is basically a large JSON file. There's an API for generating these in Spring, but you have to write that code to tell Graal, hey, this code is being called, so it needs to be included, as well as your proxies. But there's fortunately also a public repository of reachability data for popular libraries like Hibernate and Flyway that the community has contributed to. It's hosted by Oracle, I believe. So a lot of popular libraries have reachability metadata available so that they just work out of the box in your application, and Spring automatically utilizes this. So if it sees that you're using Flyway, then all of your Flyway code that should be reachable will be reachable, and it will just work without having to do anything else. The tooling will also only improve going forward. So currently, kind of the foundation has been set, and now as developers, we have to decide how we want to utilize this new technology. So it's partially up to us. So what do you have to do to get this native executable? Do I have to do a bunch of complicated configuration? Well, for the most part, you just have to do this. With Spring Boot 3, which is, of course, a requirement, you have to specify in Maven the native profile and then run the Spring Boot build image command, which creates a new image for you in Docker. The reason for this is that a lot of developers use Mac OS or Windows, but your application is likely going to be running on the server, so if you build it in Docker, which is going to be Linux, then it will run on your servers as well, because it has to be built for the right architecture, much like traditional C and C++ applications do. For Gradle, it's much the same. You just do Gradle boot build image, and you can supply some configuration on so-called build packs that Spring uses to build this for you in Docker. It also makes it much easier to do it this way because you don't have to worry about having the right Graal VM version. Currently, you need some early access version of a tool that's built on top of Graal VM, and this massively simplifies the configuration for that, because you just run this command, and provided that you have Docker, it works, and it produces a container that you can run as you would any other, just like that. So let's do a little bit of a live demonstration. I believe we have 6 to 11 minutes left, so I'm going to go through this really quick. And unfortunately, no time for questions. But you can always find me. I'll be at the stand of Chillit. I'm going to duplicate my displays. There we go. No. Keep changes, my bad. All right, hopefully you can all see this. So here we have a Spring application. Let's open the POM XML. Is this readable? Anybody? Yeah, okay. So you can see this is a Spring Boot 2.7.5 application. It has Java 11 in it. And it's pretty typical. It's just that has Spring Web and validation and data JPA with H2 embedded database, just so I didn't have to set up a database. And it's got some stuff in there, pretty typical Spring stuff. You have a controller for to-dos. And interestingly, you know, we're using JPA and everything. You see here we have the JavaX persistence packages in our database model. We let Hibernate generate the database for us. It's all pretty standard stuff. If we run this application, in WSL, which when you do it for the first time has a little bit of overhead. It takes a little bit of time, especially on battery. But after all this time, it's about 6 seconds, it started it up for us. So let's see if we can do better by utilizing Spring Boot 3. So the way I want to do that is I'm going to use a project that will rewrite our code for us, because there's a bunch of renaming that we have to do, and it's not very fun. So there's a project called Spring Boot Migrator. It's currently experimental for a Spring Boot 3.0 upgrade. And it will rewrite your code for you using Open Rewrite. It will perform a bunch of mutations. Most of the time, this gets you there, and it will just work. But there's a small chance that when it's done, you still have to fix some stuff yourself. But it's a great way to get started. So to do this, I'm going to open my terminal. And we're going to go to the Spring Boot Migrator. Thank you. I'm used to a mechanical keyboard. Let's also make doubly sure that we're on Java 17. We have no internet connection, so this might take a little bit of time. Yeah, we are on the right version, Java, jar, Spring Boot Migrator. So this opens up a little interactive shell for you to use where you have to scan your application directory, which in my case is just Spring to do. You have to let it run. Now, because we've lost our internet connection, this is going to take a little bit of time because it's going to try to connect to the internet and then fail. But what it's going to do is it's going to transform our Java version for us. So it will change this to Java 17. It's also going to change all of the packages. It's going to implement Spring milestone, the third milestone of the new Spring Boot release, and we'll upgrade that to the release candidate when it's done. Last time it did eventually work, but I think I'm just going to check out the converted version. What you would normally do is when it's done, you run apply with the migration name. It shows you a list of possible migrations. There is one that will clearly state this is for upgrading your Spring version. You have to do it, but I'm just going to check out the code instead. Great. So now this has all been generated. I wrote no additional code to do this. It just ran. And you can see that the version you use is just 3.0.0 RC1. It changed our Java version to 17. And if you look at our model from before, we're now using Jakarta packages. And if you run this all the same, it should work. So there we go. And again, it's going to take a while because we're just running it as a regular Spring application. 6 seconds again. Great. So it still works. And again, I didn't change anything. I just ran the migrator tool. It's documented on the GitHub as well. And it does most of the work for you. Try to run it and then just go into problem diagnosis to fix the remaining issues yourself. You can also give them feedback. But let's show you how you can run this as a native image. So again, this takes like 5 minutes. It's crazy. So I've done this in advance as well. I know it's a bad demo. But what you would do is you would run mvn pnative Spring Boot build image. We're just going to run that for a little bit to show you what it's doing. Actually, I take that back. What we'll do is we'll use a native profile, but we'll just do a clean package. This way, the Spring AOT engine will run, and it will generate a bunch of extra application context setup code for us that I'll show you, but it will not actually build the image, because you have to run the build image command for that. So this will still work. Oh, my bad, it's trying to connect to the internet. I can fix that though. There, that should be better. So this will generate a bunch of code for us that I'm going to show you, and then we have 3 minutes left, but it should be enough. I'll show you that you can actually run the code. So I have this already. Here you can see you just run this migration. You have the boot 2.7 3.0 dependency version update. Oh yeah, we have to use GraalVM when we're trying to do this. That's an advantage of using the build image command. You don't have to run a specific oh, great. I hope we'll get this done in time. But while that's doing its thing, I'm going to show you that if you exit this program, I can run the application. I've already built this before because I knew it was going to be difficult, especially without internet. So if you do run and you remove it afterwards, and we bind the port 8080, and then we do docker.io/library/spring to do :0.0.1-snapshot, just like that. Hopefully I typed it right. You run this, and it runs, and it starts up in about 700 milliseconds. If we just run this again, this is on a laptop with battery, 200 milliseconds. Again, this is on a laptop that's on battery, so it'll be even faster if you try to run it yourself on a proper server. And it works. So we can actually visit this API. We can go to localhost 8080. I know. Thanks, guys. We get the standard white label error page, of course, because we need a point to do one. It doesn't exist, so we get a 404 page. Of course, that's to be expected. We get Postman. Start it up. Okay. And in this case, we're doing a GET request. Again, you get a 404 error because it hasn't found this to-do. So let's create one instead. We'll do a post with a body that contains chores and, let's say, clean the kitchen. You've done this, and it creates it. And now you can see in our headers, we've got ID 1, apparently. So if we do /1 as a GET call, we can now get it back. So it works, and it was all started up. It's backed by a database, H2, JPA everything, and it works fully after starting up in 200 milliseconds, as you would expect, and no other things had to be done. I tried it, put a whole bunch of stuff into here, you know, like validation is in there, Hibernate Validator, it's all there, and it just works, and this is all you have to do in most cases. So definitely something that I think you should try out. Now again, I really want to show this, the output of this command, and then I'll let you guys have lunch. So let it run. It's doing its job, and it's running the tests. There's only one test, so that should be fine. And now, when it's done with the test, you'll see that it's going to perform some analysis. So here, it looks like it's starting up again. It's just analyzing our application context now, and it's going to use that to generate some code for us. The AOT engine will do this. So you'll find a new folder called Spring AOT, which inside of it has new sources for our package right here. You have, for instance, your application context initializer, which creates your application context programmatically, and you have this class, which contains all the beans that your application uses with code on how it needs to generate these. So it's kind of interesting, because you can see all of the different things that your application uses, but this is much nicer for Graal to analyze, because this is easy to follow. Well, easy, not for humans, but for Graal it's easy to follow. and it can recreate your entire application just like this. So this code has been generated by Spring to create your application without the use of reflection or class path scanning, so you don't have to do, start using imports instead of component scan because it's slow for Graal. It's not necessary. Spring AOT engine does it for you, and it just works. 200 millisecond startup, and you can go ham. So I think, given the time, I really need to end this. So without further ado, I would like to go back to the presentation. Thank everybody for your attention. Please rate my session in the app. I would love to get some feedback from you guys. Also, you should visit our stand from Chillit to talk to us, talk about Spring. If you have some questions for me, I'll be there. We also are thinking about doing a workshop, so if you want to play around with Spring Boot 3 yourself, go talk to us, or if you just have questions. If you want to try out our hot sauce, you can come by here. We have our own hot sauce. You can take it home with you. You can also get it at our stand if you run out. There's a bunch of other cool stuff. Definitely come check us out. We are right here. It's right across from the keynote hall. That's our stand, A2. It's basically that way. Thank you, everybody.